I've mentioned it before, but I think it bears repeating just how sideways Uranus's magnetic field is. It's so wonky that its magnetosphere, the space around the planet dominated by its magnetic field, actually opens and closes once per rotation of the planet every 17 hours or so, letting the solar wind in and then cutting it off again. And we now have some pretty compelling evidence that this creates auroras that are not only more active than any other planet in the solar system, including Earth, but they pulse in an eerie heartbeat-like fashion, shining brightly for a few hours and then fading away into the darkness, only to start over again on the other side of the planet. But let's start with the basics. Uranus is sideways. Its magnetic field is sideways, and everything that happens with its magnetosphere is also sideways. If you want to know more about why Uranus is sideways, check out this video. But basically, it has something to do with something huge crashing into the planet long ago and knocking it on its side. Now, if you're not a planetary scientist, you may be asking yourself, okay, but why does it matter? Who cares if Uranus is on its side? It's not like I can see it from my house. Well, while it might not affect you directly, it would certainly affect me if I happened to live on or visit Uranus, because, yeah, being so close to a planet when it's wobbling wildly like that gets dangerous. The sideways magnetic field carries charged particles from the Sun to the planet's poles in ways that we don't see anywhere else in the solar system. To understand what's happening, you need to get a bit of a handle on what the solar wind is. Basically, the Sun is constantly emitting a stream of charged particles, mostly protons and electrons, which flow outward from the Sun at hundreds of kilometers per second. These particles carry a magnetic field with them as they go, a magnetic field that the planet's own fields have to contend with. Earth's magnetic field, for example, is made by currents of moving charges deep inside our planet, and it's roughly the shape you'd expect. If you took a giant bar magnet and stuck it through the center of the Earth, magnetic field lines would point from the North Pole to the South Pole, wrapping around the planet. But Earth's magnetic field isn't perfectly aligned with the axis on which the planet rotates. It's tilted by about 23 degrees, and that causes all sorts of interesting things to happen. For one, the magnetic field lines coming out of the North Pole don't quite reach the equator. They're focused more toward the planet's night side. As a result, the region of space near the Earth's surface on the night side of the planet, called the magnetail, is where most of the auroras occur. That's because the charged particles of the solar wind get funneled down these open magnetic field lines and slam into the atmosphere, causing all the familiar auroral activity. Uranus's magnetic field is so wonky that it doesn't funnel particles down to the poles. It sweeps them up and then spits them back out. About half of Uranus's magnetic field lines open up into space, allowing the solar wind to pour in. On the other half of the planet, the magnetic field lines are closed, meaning that they connect from the planet's magnetic South Pole to its magnetic North Pole, without connecting to the solar wind. When those field lines are open, the solar wind can flow along them and then close back in on themselves around Uranus's equator, forming a gigantic magnetic bubble. Every 17 hours or so, as Uranus rotates, the spot where the magnetic field lines connect to the planet shifts. So half of the planet is in the bubble, and half of it is open to the solar wind. Then, as the planet rotates further, the situation flips and the other half of the planet is exposed to the solar wind, while the first half is back in the bubble. So we know that this process is happening because we can watch the way radio waves bounce off Uranus's atmosphere, and scientists have known for a while that it's causing auroras at Uranus's poles. We knew that because back in 2014 the Voyager probes which flew past Uranus back in the 1980s detected radio emissions coming from Uranus's poles that seemed to line up with the times when the magnetic field was opening up to the solar wind. But we had no idea just how weird those auroras are until now. A new study published in Nature Astronomy used data from the Hubble Space Telescope and the Chandra X-ray Observatory to look at Uranus's auroras in detail for the first time. The researchers found that Uranus's auroras are not only brighter than those on any other planet in the solar system, including Earth, but they also pulse in sync with the opening and closing of Uranus's magnetosphere. Every 17 hours, as the field lines shift, a bright oval-shaped patch of auroras appears on one side of the planet. It shines brightly for about 5 hours, and then as the magnetic field lines shift again, it fades away, only to reappear on the other side of the planet. It's like watching a cosmic heartbeat. And it turns out that these pulsating auroras are yet another piece of evidence pointing to the fact that Uranus is indeed spinning on its side. One of the co-authors of the study told me that there was some debate as to whether or not Uranus's magnetic field really did open and close like this. Some people thought that maybe the Voyager probe wasn't detecting what we think it was detecting. But the new observations from Hubble confirm that it's real. This particular study focused on ultraviolet light, which is good for seeing auroras in general, but also gives us some extra information. Specifically, the UV light that makes Uranus's auroras visible comes from oxygen and nitrogen molecules in the upper atmosphere that have been excited by the impact of charged particles. But the strength of the signal depends on the energy of the particle that hits it. So the higher the energy, the brighter the auroras shine. And the Hubble data seem to indicate that the highest energy particles hitting Uranus's atmosphere come in during the brief window, when the magnetic field lines are opening up to the solar wind. These high-energy particles only make it to an altitude of about 600 kilometers above the surface. Meanwhile, during the rest of the rotation, when the field lines are closed, lower energy particles hit the atmosphere at an altitude of about 900 kilometers. All of this extra information from the Hubble data seems to add weight to the idea that what we're seeing is driven by the opening and closing of Uranus's magnetosphere. Plus, it tells us that when those magnetic field lines are open, the solar wind is hitting Uranus at an angle, which causes the atmosphere to form these big bubbles. While studying Uranus's auroras, the team also trained their telescopes on Jupiter, Saturn, and Neptune to try and see if these same features were visible there. The results were negative. None of those planets showed the same heartbeat like auroral pulsations that Uranus did. And that makes sense, given that none of those planets have magnetic fields that twist around like Uranus. So it looks like this feature is probably unique to Uranus. Now, if you ask me, this discovery raises a lot more questions than it answers. Like what exactly is going on down there to cause this heartbeat effect? And what are the long-term effects of these intense auroras on the planet's atmosphere? Unfortunately, getting answers to those questions will have to wait until we send a probe to Uranus. NASA has considered sending a probe to Uranus as part of its flagship Discovery program, but as it stands, there's no firm plan to do it yet. I mean, we still haven't gone back to the moon. So I wouldn't hold your breath. Meanwhile, though, you can enjoy the view. Uranus is visible with the naked eye from Earth, though it looks like just another star. If you have a telescope, you can find it in the constellation of Pisces, the fish. It'll appear as a tiny disk, sideways, just like its magnetic field. Thanks for watching this episode. If you liked it, you can leave a like. You can leave a dislike if you didn't. You can check out our other videos. You can comment with video suggestions down below. And don't forget to subscribe.